Wind speed estimates exceed 20 knots.
Confirmed. The fuselage is vibrating excessively.
Make a note of the wing deflection at this velocity.
The stress right here is too high. We need to reinforce this joint.
Look at this section instead. I have a solution for the bracing.
If we commit the reserve divisions here, Montgomery's supply lines become vulnerable. We need air superiority over the channel. Adjusting the pitch now. Power input is fluctuating. Keep it steady. Airspeed is holding steady at Mach 0.8.
Lift coefficient is dropping faster than expected.
Wait, look at the strain gauges on the starboard wing mount.
January 1941. The wind bites across an empty airfield in Dayton, Ohio. Snow-dusted hangars creak under the weak winter sun. A lone biplane sits tethered, wings trembling as if impatient to soar. Engineers, bundled in heavy coats, circle it, notebooks in hand, eyes scanning the skies for a breath of natural wind. The roar of distant traffic and the faint hiss of early engines fill the crisp air. Here, in this quiet tension, America faces a silent problem. The skies promise war, but the machines are untested. Aircraft cannot simply be sent aloft without knowing how they will respond to turbulence, lift, and drag. Yet there are no towering wind tunnels, no artificial gales to simulate the storms of combat. Inside a modest workshop, the descendants of the Wright brothers hunch over crude diagrams. Wood, steel, and electric motors stand ready, but the challenge is immense. How do you teach a plane to fly when the wind itself is absent? The answer, as impossible as it seems, is about to be born here. Wind machines, a legacy of invention meeting the urgent call of war. By 1941, the world was already at war. Europe had been engulfed for over a year, with German panzer divisions rolling through France, the Luftwaffe dominating the skies, and the British Isles bracing for relentless aerial assault. Across the Atlantic, the United States remained officially neutral, but neutral in name only. Military planners knew that conflict was inevitable, and the skies would soon demand an American response. Yet, America's air forces faced a glaring deficiency. The nation's aircraft were untested for the demands of modern warfare. Planes were designed and built, yes, but there were no facilities to rigorously test their performance in controlled conditions. Natural wind patterns dictated experiments. Pilots risked early flights on uncertain aerodynamics. Gliders, biplanes, and prototypes relied on open fields and fair weather for critical tests. The threat of accident or catastrophic failure was constant. It was here that the legacy of the Wright brothers came sharply into focus. Decades earlier, in the sands of Kitty Hawk, North Carolina, Orville and Wilbur Wright had first conquered controlled flight. Their triumph was not merely a technical achievement. It was a demonstration of methodical experimentation. The brothers measured, calculated, and repeated trials, noting the slightest variations in lift and drag. They had invented more than an aircraft. They had invented the principles of testing. By the late 1930s, the U.S. military still leaned heavily on their methodologies. The Army Air Corps and the Navy understood that combat-ready aircraft required controlled aerodynamic testing, but funding and infrastructure lagged behind ambition. In practical terms, engineers lacked the mechanical wind to simulate high-speed flight indoors. It depended on outdoor conditions, gusts, breezes, and luck. A sudden change in weather could ruin days of careful measurement, sometimes with catastrophic consequences. Wartime urgency only heightened the problem. Europe's air battles were teaching stark lessons. Planes untested under extreme conditions failed in combat. Pilots could no longer rely on improvisation alone. The U.S. needed a solution to accelerate experimentation, to transform unproven prototypes into reliable war machines. It was in this environment that the idea of artificial wind began to emerge. Engineers envisioned machines capable of generating strong, consistent airflow, turbulence controllable, speeds adjustable. The concept was simple in theory, but complex in execution. The machines would have to mimic nature itself, replicate wind, vortices, and air pressure at scales that small laboratories had never attempted. These were not mere fans. They were precision instruments designed to teach aircraft how to fly before a pilot ever left the ground. The military's interest was immediate. By 1940, the War Department had begun consulting engineers with expertise in aerodynamics. Names of early innovators resurfaced from dusty files. Men who had worked with the Wright brothers, engineers who had studied at NACA, the precursor to NASA, and inventors who had designed wind tunnels for gliders in the 1920s. Their brief was urgent. Build a machine that could replace the wind itself. Across small workshops, wooden baffles, motors, and copper wiring began to form the skeletons of experimental wind devices. Some prototypes were simple, rotating fans and reinforced frames, but others embraced complexity. Adjustable ducts, velocity controls, and measurement instruments capable of capturing every nuance of airflow. These machines were intended not merely to move air, but to teach it, to allow scientists and pilots to observe, record, and refine aircraft performance in ways nature had never permitted. Still, skepticism was rife. Could an electric fan truly replicate the wind? Could these machines prepare an aircraft for the unpredictability of combat skies? Pilots and engineers alike watched the first tests with a mixture of hope and anxiety. Success would mean a leap forward in American aviation. Failure could delay the nation's preparedness by months, even years. The problem was clear. America had airplanes, engineers, and ambition, but no wind. And in 1941, the race to prepare for the skies of war was already underway. The solution would require ingenuity, precision, and the enduring legacy of the Wright brothers' principles: test, measure, refine. In this challenge, the United States stood on the threshold of a quiet revolution, a revolution that would shape its air power for decades to come. This growing tension between necessity and innovation naturally led to the next stage: designing machines that could finally control the wind itself. The challenge of creating artificial wind was deceptively simple in words, yet fiendishly complex in practice. Early prototypes often failed within hours of testing. Fans would overheat, wooden frames splintered under stress, and airflow patterns proved far more chaotic than anticipated. Engineers discovered quickly that producing consistent wind was only half the battle. Measuring it accurately was equally critical. Without precise instruments, a gust could not be differentiated from the machine's intended output. It was here that the Wright brothers' legacy proved invaluable. Though Orville and Wilbur had passed from active invention decades earlier, their notebooks, technical diagrams, and experimental philosophies remained in circulation among aeronautical engineers. The Wrights had emphasized rigorous measurement, repeatability, and observation of subtle airflow effects, principles that now guided wind machine development. Every prototype incorporated lessons drawn from their work: slotted ducts, variable speed rotors, and carefully calibrated air velocity sensors. By mid-1941, several workshops in Dayton and the surrounding Midwest had become laboratories of ingenuity. Engineers experimented with scaled-down aircraft models mounted on adjustable stands, observing lift, drag, and stall characteristics under controlled airflow. Early tests revealed the limits of conventional fans. Turbulence was uneven, velocities too low, and energy consumption unmanageable. Yet these failures were instructive. Each broken rotor, each cracked duct, taught designers more than months of trial flights in unpredictable weather could. The U.S. military took notice. NACA, then America's premier aeronautics research organization, began supplying technical guidance, while the War Department funded expanded experiments. Military engineers realized that these wind machines could accelerate aircraft development in ways previously unimaginable. Instead of waiting for a windy day on an airfield, a pilot could test maneuvers indoors under controlled, repeatable conditions. Designs could be adjusted in real time and aerodynamic flaws identified before the first manned flight. Innovation was not limited to mechanical design. Electrical engineers developed complex motor systems to produce steady airflow, while material specialists tested reinforced alloys and hardwoods capable of withstanding prolonged stress. Some machines used multiple fans in tandem, creating variable wind speeds and simulating turbulence at high altitudes. Sensors measured every nuance of airflow, feeding data to engineers who refined wing shapes, control surfaces, and fuselage contours. By late 1941, small-scale wind tunnels were operational across several military and private facilities. These were modest compared to modern standards: narrow metal corridors, buzzing with the constant roar of motors, but they marked a turning point. American engineers could now replicate conditions once left entirely to nature. The nation had transformed a fundamental limitation into a tool of precision. Yet the process was not without tension. Military leaders demanded results quickly, anxious to match Axis powers in aircraft performance. Engineers worked long hours, often in bitterly cold hangars, adjusting rotors, recalibrating sensors, and retesting models. There were moments of doubt. A prototype might fail on the eve of a critical demonstration, or measurement error could send an aircraft design in the wrong direction. Still, progress was steady. Each successful test brought the United States closer to a state of readiness that would prove essential once war arrived. By the end of 1941, the first full-scale wind machines capable of testing real aircraft were nearing completion. These machines were, in essence, mechanical storms under human control. Engineers and pilots watched as wings flexed, fuselages shivered, and propellers responded to controlled gales. The airfields outside no longer dictated experimentation. Inside these machines, flight could be dissected, understood, and perfected. The implications were profound. The United States was no longer at the mercy of nature. Testing had become a science, a controlled environment where innovation could proceed at unprecedented speed. Designs that might have taken years to refine outdoors could now be perfected in months. The nation's air power was on the cusp of transformation, built on a foundation of careful measurement, mechanical ingenuity, and the enduring guidance of the Wright brothers. This technical evolution set the stage for the angles we will explore next. Human, technological, tactical, and moral perspectives that together illuminate the full story of America's leap from untested aircraft to controlled mastery of the skies. In a cramped Dayton workshop, the hum of motors filled the air. Engineers leaned over wooden models, pencils scratching across yellowed paper, eyes narrowed in concentration. These men were descendants, in spirit if not in blood, of the Wright brothers. Innovators trained to see flight as a puzzle to be solved with observation, mathematics, and tireless trial. For them, the absence of natural wind was more than an inconvenience. It was a challenge to their ingenuity, a riddle demanding a mechanical solution. Nights were spent calculating rotor speeds, angles of airflow, and duct shapes. Days were consumed with assembling and disassembling prototypes, noting every vibration and deviation. The human toll was real. Frozen fingers from winter hangars, sore backs from bending over frames, eyes strained under dim lighting. Yet failure was rarely discouraging. Every broken rotor or miscalculated gust offered a lesson, a clue toward the next breakthrough. These engineers were aware that their work carried weight beyond the workshop. The planes they tested would one day carry pilots into combat, into skies dominated by enemy fighters. Each measurement, each adjustment was a quiet act of preparation for the inevitable. The human element, perseverance, curiosity, and meticulous care was the force that drove machines into the future. The wind machine was not a simple fan. It was a mechanical simulacrum of nature itself. Large metal corridors echoed with the roar of electric motors, the air vibrating with controlled turbulence. Engineers experimented with rotor placement, duct shape, and fan speed, learning how airflow interacted with miniature models. Sensors recorded lift, drag, and pressure points with precision that no open-air test could achieve. Early designs were rudimentary. A single rotating fan, a narrow channel of airflow, a simple support for a glider. But progress was relentless. Multi-fan arrays created adjustable velocities. Slotted ducts simulated turbulent air. Instruments captured every fluctuation. The Wright's principles of measurement guided each refinement, ensuring repeatability and accuracy. The technological breakthrough was not merely in airflow. It was in controlled simulation. Conditions could be repeated exactly, variables isolated, designs iterated rapidly. Wings could be reshaped, fuselages adjusted, control surfaces modified, all without risking pilot lives or waiting for unpredictable weather. The wind machine became both a teacher and a laboratory, translating the chaos of nature into knowledge. Military planners understood that aircraft performance would determine outcomes long before the first bullet was fired. Dogfights, bombing runs, and reconnaissance missions depended on machines performing flawlessly under stress. Delays in testing could leave the U.S. Air Corps lagging behind the Luftwaffe or the Royal Air Force. Wind machines offered a solution. Engineers could now refine designs indoors, accelerating production timelines. Pilots could train on models that faithfully represented the stresses of high-speed flight. Tactical decisions, from formation strategies to load capacities, could be informed by precise data instead of conjecture. Each successful test meant a plane that could maneuver as predicted, a mission more likely to succeed, and a life potentially saved. The broader tactical impact was also psychological. Commanders could plan with confidence, knowing that their aircraft had been tested rigorously. The invisible war of preparation, data collection, simulation, refinement began to level the playing field against nations that already dominated the skies. In this sense, wind machines were weapons of strategy, shaping victory long before combat began. Behind the scenes, military leadership monitored progress with keen interest. The War Department and NACA provided funding, oversight, and technical guidance, but they could not dictate the detailed calculations or mechanical intuition required. Leadership required patience, trust, and discernment. Qualities tested as prototypes failed, motors burned out, and measurements fluctuated unexpectedly. Leaders recognized the Wright brothers' principles as a foundation for modern engineering, encouraging engineers to experiment, observe, and iterate. Some generals visited Dayton personally, walking the workshops, asking questions, and witnessing demonstrations. They understood that innovation could not be rushed, yet urgency pressed constantly. The world was at war, and America could not afford delays. Decisions made in offices and laboratories shaped the future of aerial warfare, approving funding for large-scale wind tunnels, allocating skilled engineers, and prioritizing prototypes for testing required foresight and conviction. In many ways, leadership was the silent partner in innovation, providing resources, vision, and patience to those who labored tirelessly over fans, rotors, and models. Across the Atlantic, Germany's Luftwaffe was refining aerial tactics with deadly efficiency. Messerschmitts and Heinkels dominated the skies, and pilots honed maneuvers that exploited every aerodynamic advantage. Britain's Royal Air Force, battered yet resolute, relied on extensive flight training and carefully engineered aircraft to repel assaults. In this context, the United States could not afford to send untested planes into combat. The stakes were clear. Failure to innovate risked strategic inferiority. If American aircraft were inadequately tested, pilots might encounter stalls, structural failures, or control issues in the heat of battle. Every day, without controlled testing, delayed readiness, potentially giving Axis powers a decisive advantage in the air. Engineers and military leaders were keenly aware that a single design flaw could have consequences measured in lives and territory. Wind machines, therefore, were not merely mechanical curiosities. They were instruments of national defense. By simulating high-speed airflow, turbulence, and aerodynamic stress, engineers could refine aircraft before they ever left the ground. This preemptive advantage allowed the U.S. to close a technological gap that might otherwise have been exploited by the enemy. In a global contest of speed, precision, and preparation, controlling the wind became a quiet but critical battlefield. Beyond mechanics and strategy lay a deeper, human question. What does it mean to invent under pressure? The Wright's philosophy emphasized meticulous experimentation, patience, and careful observation. Yet in 1941, time was scarce. Engineers faced the moral tension of balancing perfection against urgency. Could a machine be tested quickly enough to serve the nation without compromising safety? Society watched silently. Reports in scientific journals and military briefings noted progress, but few understood the stakes. Every measurement taken, every rotor adjusted, carried an ethical weight. Pilots' lives depended on the accuracy of these tests. Engineers became guardians not just of technology, but of human survival. Their work reflected a national ethic, ingenuity as a moral obligation in the face of existential threat. This moral dimension extended to the public imagination. The narrative of American ingenuity, solving the impossible, harnessing science to protect lives, resonated far beyond Dayton workshops. Wind machines were more than tools. They were symbols of resilience, intelligence, and collective responsibility. In mastering the air artificially, America demonstrated that necessity could be a catalyst for ethical, transformative innovation. It was early 1942. Though the United States had only recently entered the war, the groundwork for its aerial preparedness had been laid months earlier in quiet workshops. In a long, narrow laboratory in Dayton, engineers gathered around the first full-scale wind machine capable of testing complete aircraft. The room buzzed with anticipation, motors humming like restrained storms, air ducts ready to channel controlled gales. Outside, winter winds howled across the barren airfields, but inside, humanity sought to command the sky itself. The first prototype, a sleek fighter model mounted on a reinforced stand, trembled as the fans roared to life. Sensors ticked, gauges fluctuated, and the engineers watched every flicker of motion in wings, fuselage, and control surfaces. This was not mere demonstration. It was a test of survival. Every measurement could determine the difference between an aircraft that would fly in combat and one that would fail catastrophically. The tension was palpable. Engineers whispered corrections, adjusted rotors, recalibrated instruments. Pilots, present as observers, held their breath. They had trained in simulators and open fields, but this controlled storm promised to reveal secrets of lift, drag, and stability that no natural gust could provide. When the wind reached its operational velocity, the aircraft responded perfectly. Wings flexed as designed, ailerons and elevators moved precisely, and the model held its line against turbulence that mimicked the skies over Europe. It was a moment of triumph, but also a turning point. The success validated years of meticulous experimentation and design. Failures that had seemed insurmountable, motors burning out, turbulence destabilizing models, measurement errors, were now lessons converted into mastery. Engineers began running repeated cycles, each slightly faster, each slightly more turbulent, pushing the boundaries of what was possible. By the end of the day, every system had been tested to its operational limit, data meticulously recorded, and confidence steadily rising. This breakthrough had immediate consequences. The Air Corps could now refine aircraft designs indoors, iterating far faster than any reliance on natural wind could allow. Prototype fighters and bombers were modified based on precise measurements rather than educated guesses. Training protocols adapted, incorporating lessons from controlled airflow tests. For the first time, American engineers and pilots felt that the skies, once unpredictable, dangerous, and merciless, could be understood, anticipated, and mastered. Yet, even in this triumph, risk lingered. Engineers recognized that real combat conditions would never perfectly mirror the laboratory. Gusts, crosswinds, and enemy maneuvers introduced unpredictability. Still, the wind machine represented a quantum leap forward, It was a tool that could replicate natural forces on demand, producing results unattainable in open-air experiments. By taming artificial wind, America gained a tactical advantage invisible to the enemy, but critical to its future air campaigns. The emotional weight of the moment was unmistakable. Engineers, many who had labored through bitter winters and countless failures, allowed themselves brief smiles, nods of approval, even quiet laughter. Pilots felt relief tempered with awe. They could now approach aircraft with knowledge, not blind faith. And military observers, present in understated yet keen attention, began to understand the broader implications. This was not simply a technological victory, but a shift in the nation's ability to wage war effectively from the air. Data gathered from these tests informed immediate design revisions. Wing shapes were adjusted, control surfaces refined, and structural integrity verified under conditions mimicking extreme flight. Every failure had been analyzed, every success reinforced. By controlling wind, engineers controlled knowledge, and with knowledge came speed, reliability, and confidence. This first successful series of tests was more than an engineering milestone. It represented the convergence of decades of aeronautical theory, hands-on experimentation, and national urgency. The Wright brothers' ethos, careful observation, meticulous measurement, iterative improvement, had reached its fullest expression. The dream of mastering the skies, once constrained by natural forces, now depended on human ingenuity alone. The breakthrough concluded with a sense of quiet determination. Engineers and pilots alike knew the stakes had shifted. Failure was no longer an abstract possibility. The next challenge was scale, applying these lessons to multiple aircraft types, larger models, and eventual mass production. This would test the limits of engineering, resource management, and human perseverance in ways no single wind tunnel had yet attempted. And it was precisely this challenge that set the stage for the next, most intense phase, scaling up wind machines to full military application, transforming controlled tests into operational readiness, and preparing America's air power for the reality of global war. By mid-1942, the first operational wind tunnels capable of testing full-size aircraft were running at several military facilities. Dayton's experimental workshop had grown into a network of laboratories, each designed to push the limits of speed, lift, and structural endurance. Pilots, engineers, and military observers converged to witness the next phase, controlled testing of planes that would soon face enemy skies. The first full-scale fighter, mounted securely in a reinforced chamber, faced airflow velocities exceeding 150 miles per hour. Motors roared, and air ducts vibrated under the strain. Engineers monitored gauges, recorded minute fluctuations, and adjusted fan angles to simulate turbulence at multiple altitudes. Pilots, seated in mock cockpits, manipulated controls with tense precision, watching instruments react to each input. This was no simulation. It was a dress rehearsal for war, conducted in a metal corridor where nature itself had been tamed. The results were immediate and transformative. Previously untested behaviors, wing flutter at high speed, control surface oscillations, fuselage resonance, were identified and corrected before a single man flight. Designs that might have required months of outdoor trial and error were refined in weeks. The military could now certify aircraft as combat-ready with unprecedented confidence, shortening the timeline from prototype to frontline deployment. The psychological impact was equally profound. Engineers and pilots felt a surge of cautious optimism. Years of labor, failure, and incremental progress culminated in tangible achievement. Machines responding exactly as predicted, data aligning with expectations, and every variable under precise control. Military leaders recognized that America had gained an invisible advantage. While Axis powers continued relying on field testing in natural conditions, U.S. forces were now armed with certainty, precision, and foresight. Challenges remained. Early full-scale tests occasionally produced near disasters. Motors overheated under prolonged operation, ducts warped under intense airflow, and some aircraft experienced unexpected oscillations. Yet each problem was met with rapid analysis, repair, and retesting. The iterative process, a hallmark of the Wright's methodology, ensured that every setback was temporary and educational. The combination of engineering rigor, mechanical ingenuity, and disciplined observation created a system far more resilient than any single machine. Operational wind machines also influenced pilot training. Aviators could now practice maneuvers and emergency responses in controlled conditions that faithfully mirrored real-world flight. Stalls, spins, and rapid climbs could be observed, measured, and corrected safely. This reduced the learning curve for combat pilots, saving lives and improving mission effectiveness. Wind tunnels became classrooms, laboratories, and testing grounds all at once, where theory met practice and mistakes could be contained without fatal consequences. By late 1942, the results of these efforts began to ripple outward. Aircraft designs across the Army, Air Forces, and Navy incorporated insights gained from wind machine testing. Fighter planes became more agile, bombers more stable, and reconnaissance aircraft more reliable. Industrial production adjusted in response. Wings, fuselages, and control surfaces were manufactured to precise specifications refined under artificial airflow. Every machine leaving the assembly line carried the imprint of controlled, measured wind, a silent but critical contributor to operational readiness. The human drama persisted alongside technical achievement. Engineers worked long hours, often late into the night, refining calculations, replacing worn rotors, and verifying sensors. Pilots sat in test cockpits, muscles tense, eyes scanning instruments, fully aware that success here would translate into life or death in combat. Military leaders oversaw the process with vigilance, balancing the need for speed against the risk of catastrophic errors. The laboratory had become a battlefield of intellect, endurance, and precision. The culmination of these efforts marked a turning point in American air power. No longer were engineers and pilots at the mercy of unpredictable winds. Knowledge, skill, and mechanical innovation had created a controllable environment where aircraft could be perfected before taking to the skies. By mastering artificial airflow, America had transformed a limitation into an advantage, a quiet, invisible victory that would shape its aerial campaigns for the remainder of the war. The success of full-scale wind machines was more than technological. It symbolized the marriage of human ingenuity, rigorous scientific methodology, and urgent necessity. From the first Gus and Dayton workshops to the roaring tunnels of military laboratories, the journey had tested skill, patience, and resolve. and it set the stage for the next chapter. The aftermath, the measurable impact on aircraft production, pilot readiness, and America's strategic position in the skies over Europe and the Pacific. By early 1943, the first American aircraft refined under wind machine testing were rolling off assembly lines. Fighters, bombers, and reconnaissance planes moved from workshop prototypes to operational units with unprecedented speed and reliability. Data from controlled airflow experiments had reduced design errors, minimized in-flight failures, and ensured that pilots could trust the machines in combat conditions that had once been unpredictable. The impact was immediate. Squadrons equipped with these aircraft reported higher mission success rates during training exercises. Maneuvers that previously required multiple trial flights could now be executed flawlessly on the first attempt. Pilots, having studied performance under controlled turbulence, experienced fewer in-flight surprises, reducing accidents and boosting morale. Aircraft handling improved noticeably, with sharper turns, more stable dives, and precise responses to control inputs. Military production itself benefited. The precision insights gained from wind machine testing allowed manufacturers to standardize components, reducing waste and improving efficiency. Wing profiles, fuselage shapes, and control surfaces were optimized before production, avoiding costly rework. The speed from design to deployment accelerated dramatically, ensuring that America could field competitive aircraft while European battles raged. Engineers and pilots alike recognized the human dimension of these achievements. The countless hours spent in Dayton's hangars, enduring cold winters, failed tests, and mechanical frustrations, had yielded tangible results. For the first time, American air power was built on controlled science rather than chance. The labor, meticulous observation, and relentless iteration had transformed uncertainty into precision. Operational readiness extended beyond individual aircraft. Wind machine testing allowed for informed tactical planning. Commanders could anticipate aircraft performance, predict fuel consumption, and refine formation strategies. Intelligence reports could be paired with measured performance metrics, giving the United States an advantage in both planning and execution. Aircraft were no longer experimental tools. They were reliable instruments of war, tested in conditions that closely approximated the battlefield. The success was noted in official reports. By mid-1943, NACA and the Army Air Forces documented measurable improvements. Flight stability increased by over 20% in tested designs. Takeoff and landing reliability rose significantly, and pilot training hours required to achieve basic competency decreased. These were not abstract numbers. They reflected lives saved, missions completed, and equipment preserved. Perhaps most importantly, the wind machines established a culture of scientific rigor within American aviation. Engineers, pilots, and military leadership now shared a common framework. Test thoroughly, measure precisely, and refine continuously. This methodology, rooted in the Wright brothers' philosophy, became the foundation for post-war aviation research, influencing everything from jet development to aerodynamic studies for decades. The immediate aftermath of the wind machine program was not flashy. There were no public parades, no dramatic announcements in newspapers. Yet the impact was profound. Aircraft were safer, pilots more confident, and military planners better informed. The unseen laboratories and quiet workshops had quietly reshaped the nation's air power. The next stage of the story examines the broader consequences, long-term strategic shifts, industrial momentum, and the enduring legacy of the Wright-inspired innovation that transformed American aviation. As 1944 unfolded, the full impact of America's wind machine program became unmistakable. Aircraft production had scaled massively, fueled by precise data and refined designs. Every new fighter, bomber, and reconnaissance plane carried the imprint of controlled airflow testing. Engineers had learned to anticipate structural stress, optimize lift, and adjust control surfaces before a single pilot took to the skies. In doing so, the United States had transformed its industrial capacity into a weapon as decisive as any bomber or fighter. The benefits extended far beyond mechanical performance. The accelerated design cycle allowed the United States to field aircraft at a pace unmatched by Axis powers. Lessons from wind machine tests informed modifications to existing models, ensuring that even older planes could meet evolving combat demands. Pilots entered training confident in the capabilities of their machines, and commanders could plan operations based on reliable, predictable performance data rather than assumptions or trial-and-error experience. Strategically, this invisible advantage reshaped the war effort. U.S. air power became increasingly decisive in both the European and Pacific theaters. Fighter squadrons, optimized for maneuverability and endurance, provided cover for bombers that struck deep into enemy territory. Reconnaissance aircraft delivered accurate intelligence, thanks to aerodynamic refinements that improved stability and range. Every mission, every sortie, was a testament to the unseen work of engineers and the controlled winds that had made precision possible. Industrial momentum also accelerated technological innovation. The principles learned in wind tunnel testing laid the groundwork for jet aircraft, long-range bombers, and experimental designs that would define post-war aviation. Engineers who had cut their teeth on these machines went on to shape the emerging aeronautical industry, applying lessons of measurement, iteration, and controlled testing to new challenges. The United States had not just caught up, it had leapfrogged into a position of long-term technological dominance. The human impact persisted alongside the technical. Engineers, pilots, and military leaders took pride in a quiet, cumulative achievement. Success was measured not in headlines, but in mission readiness, in lives preserved, and in machines that performed exactly as expected. Observers later noted that the culture of rigorous testing and meticulous engineering became a defining feature of American military aviation. It was a legacy born of necessity, guided by principle, and executed with precision. By the end of the war, the wind machine program had proven its value beyond question. Aircraft designs tested under controlled airflow had lower failure rates, higher combat effectiveness, and contributed directly to operational success. While battles were won in skies far from Dayton's workshops, those controlled corridors of wind had shaped every critical decision, every reliable flight, and every measure of American air power. In the broader sweep of history, the program also highlighted the interplay between ingenuity, urgency, and systematic experimentation. The United States had faced a fundamental limitation, the absence of natural wind for testing, and turned it into an advantage. The result was not only a more effective Air Force, but a template for innovation under pressure, a lesson that would influence military and civilian aeronautics for decades. This long-term transformation naturally leads to reflection, the calm, philosophical closure that considers what these machines and the people who built them meant for history, technology, and humanity itself. The wind machines of Dayton were never meant to make headlines. They were quiet instruments of precision, humming in dimly lit workshops while the world burned overseas. Yet their impact was profound, invisible but undeniable. In those corridors of controlled airflow, America learned a simple truth. Mastery of nature begins with understanding it. Engineers, pilots, and military leaders had faced a fundamental limitation, the absence of wind, and turned it into opportunity. They transformed uncertainty into knowledge, trial into measurement, and failure into insight. In doing so, they created a system that ensured aircraft would perform as intended when it mattered most in the chaos of battle. The work was meticulous, unglamorous, and often exhausting, but it carried the weight of lives and the stakes of nation. The legacy extended far beyond the war. Wind machines became the foundation for modern aeronautics, guiding the development of jet engines, supersonic flight, and space exploration. They embodied the Wright brothers' enduring philosophy that careful observation, repeated testing, and disciplined innovation can overcome even the most stubborn obstacles. What began as a response to a simple scarcity, the absence of natural wind, had reshaped aviation forever. Yet perhaps the most striking lesson is human. Faced with pressure, engineers did not cut corners. Pilots trusted their machines because they had been tested, measured, and perfected. Leaders invested in patience and process. Together, they demonstrated that ingenuity thrives not in haste, but in careful, deliberate action, even when urgency presses hard. The Dayton wind machines remind us that history often turns on small, controlled moments rather than dramatic battles. In the quiet hum of a laboratory, in the precise measurements of air flowing over a wing, America built a bridge between human intellect and the sky itself. It is a story of curiosity, perseverance, and the invisible force of preparation, a testament to the idea that sometimes the most powerful victories are won long before the first shot is fired. And in mastering the wind, humanity glimpsed the possibility of mastery over the unknown, a lesson as timeless as flight itself.